know. I mean, I would really feel terrible if Mike can't come here, but it, you know.
We usually have the same.
Yes.
Well, I'll just talk with Margaret. He's still available.
Okay.
The odds are quite good at this point. I mean, he has one more interview to do this week.
Quality is not good.
Oh, but are we gonna wait?
Oh.
Yeah, because you have to wait for him and his family to come visit the. It's, you know, it's a kind of, I mean, it's, I think when the offer is made, I mean, people needs to work on offer after the offer is made, we'll probably do my kind of short.
It's fine, it's
You know, you can't do that anyway, so it's all theoretical.
But still. Couple weeks.
Something like that. But in from the point of view of Mike, he's not on the market, so.
No, I understand
Yeah,
that.
so.
Gonna get better.
Yeah, we'll find out.
I think so.
But I mean, the overlap
it's
with
only one.
Mike
one
was
thing.
actually, the overlap with Pat, it's not just supernova, it's peculiar supernova that Pat, you know, it just. It's just, you just can't argue against.
Hello?
that. That's-
Hello?
that's for the future
Hello?
of the department.
Oh.
That's higher.
I don't have my microphone. I don't have microphone.
Okay.
Oh, there are two other guys.
Oh, we just, the DEI. What are we? gonna
Hello?
do?
Hello? Hello, can you hear me? Hello, can you hear me?
Or you might ask, what are you doing?
No sound.
Huh? Can you hear me? Yeah, but yeah, that's a bit weird.
The open house.
Oh.
You'd like, you know, there's many.
So people on Zoom cannot speak. You mean?
Hello? Hello? Hello?
We can hear you.
Yeah.
Just to be well established.
But also
Right.
Yeah. It's kind of complicated. Usually we have the same on top floor. It was the old.
Something that controls for me.
Yeah.
I haven't seen him.
What is that? Is that? Doesn't make you know what I'm gonna say. Oh, what if? That's just like. DMO.
People come.
Very nice. People are not straight.
Sorry.
No.
I got your side.
What are you doing? Very. Not the same, but.
Just for a
Yeah.
But they sound good. Thank you for the effort here.
Also the audio.
Big, he wants to test the audio.
Get on far away so that we cannot hear.
Yeah, go.
Or something.
We get 2 8s.
I was.
Just
Okay. Okay.
Yeah.
They have different.
So I think now we can start. So today we are happy to have Nadav, he his PhD from Tel Aviv University, and he's now doing postdoc at UC Berkeley, and this is, I believe, his second year, right? Yeah. And he's going to tell us today. He's going to tell us about 21st meter and some data baryon interaction. So please.
Hi everyone, and thank you for inviting me. It's first time I see snow this year. So,
You come next month, you'll probably see it.
Okay. Well, so, but they told me today it's like almost summer, right? So it's about freezing.
Yeah.
Anyhow, I'm happy to be here. Everything looks very lovely so far. Yeah, so today I'm going to be talking about 21 centimeter cosmology, but from a particle physicist point of view. And I'm not going to sell you anything big. This whole talk can be viewed as somewhat pessimistic, but for a good reason. I mean, there was a lot of work, a lot of effort involved in learning what can and cannot be said about particle physics using 21 centimeter cosmology. And there will be other things that can be said using 21 centimeter cosmology and particle physics, but specifically this talk is going to focus on interactions and more specifically elastic interactions between dark matter and baryons and how those can imprint 21 centimeter cosmology. So there is still hope that we might say something, as I'm going to show towards the end of this talk, but a lot of it is going to be like a broad intro to this field and why we know now that the range of possible things that can be probed using 21 centimeter cosmology is not as wide as people thought when particle physicists started thinking about this in, well, some people started earlier, but most of the field started talking about it in 2018, following the edges anomaly that we'll describe soon enough. So the plan for today is going to be to describe some basic features of 21 centimeter cosmology and how can we understand the cosmological evolution of this line that we are talking. I will then present the edges height and how SARAS-3 broke this hype or made it go away, at least in the eyes of some people. And I think that Wally told me that actually there was never a hype, because once you have the experiments that tell you, that give you empirical evidence for two different things, you need to ask which one is correct, and I think they are both equally correct. Then we'll talk about dark matter baryon scattering in 21 centimeter cosmology. And after we'll narrow down drastically the amount of models I think can be probed using this new observable, I will present a new possible smoking gun for the one model I think is still relevant for this kind of thing, which is a more recent one that I put out a couple of months ago. Okay, so why should we care, or why should we wish to measure this 21 centimeter line? And the reason is that we want to understand the cosmological evolution of the universe. This is at least what cosmologists aim to do. We as particle physicists might be interested in a more particle physicist point of view of the evolution of the universe, but in principle, this whole program exists because we want to measure the universe, study the cosmological evolution of the universe. Now, CMB is a great tool, but it is sensitive to a very limited redshift interval around recombination, where this last scattering happened. But we also have more recent measurement that allows us to measure the large-scale structure of the universe, which comes from galaxy surveys. But once again, in order to measure galaxy distribution and the structure and the way in which they are scattered around space, we need galaxies to exist. And this happens later in the evolution. And for most cosmologists, we can say that it happened roughly today, right? And there is a huge volume of universe, a huge time interval, a very long time interval between CMB and those later galaxies that is currently, well, to some extent, not at all probed. And one very nice thing about this epoch is that during this epoch, or few epochs, the universe is cold, and it is so cold that most of the standard model bath is in the form of hydrogen atoms, well, also photons and neutrinos, but important for this talk, there is a large fraction of it in the form of neutral hydrogen atoms. And if we could measure somehow something about these hydrogen atoms, we get a new window into a very large, very long epoch of the universe from recombination up until reionization. Okay, so what can we observe, assuming we have a huge volume of hydrogen atoms? And the answer is something that we call the brightness temperature. So how is this brightness temperature related to 21 centimeter, or the hydrogen atom in general, it is related through the fact that the hydrogen atoms, or the ground state of hydrogen atom, is split into two hyperfine states, the CO4, a triplet state and one singlet state, and they are differ from one another by a very small energy difference of 6 micro eV, and the wavelength of a photon that is absorbed or emitted in those hyperfine transition has a wavelength of 21 centimeter, and that's the reason we call it 21 centimeter cosmology, because we are going to look for absorption and emissions of this 21 centimeter photon. Now, an important number that we're going to discuss a lot in this talk is this PS in pink over here, which is called the spin temperature. And the spin temperature is not a temperature. Why do we call it a temperature? Because it is convenient. What the spin temperature is a good measure of the relative abundance of number densities of triplet and singlet in a given chunk of gas. Right, so I have a gas of hydrogen atoms. Some of it will be in the triplet state, some of it will be in the singlet state, and the relative abundance is given through this pseudo thermal variable that we call the spin temperature. Okay, why is the spin temperature convenient? This is what we're going to describe next. Right, so imagine I have a cloud of hydrogen atoms with a relative abundance of triplet to singlet atoms. That defines a given spin temperature. Now I have an incoming flux of photons, and their intensity is given by I gamma of F, the frequency, and it travels through this hydrogen atom cloud, and the spectrum that leaves this hydrogen cloud is given by I prime of F. Okay, so the intensity prime. Now, anything that happens to those photons happens very close to this 21 centimeter frequency, 1/21 centimeter. So instead of talking about this whole distribution, the entire intensity of photons, we're going to now focus only on the intensity at the 21 centimeter line. Okay, so specifically at the frequency of 21 centimeter photons. Now, in all the discussion to follow from here onward, we always in temperature that are much higher than this 6 micro eV. So if we have an intensity of photon, which is given by some black body distribution, we don't need to talk about the whole distribution. We can just approximate it in low frequencies and use this formula to relate the intensity to the temperature through the so-called Reionization law. Right? So we are looking at energy much below the temperature, so we can use the Reionization formula. So the intensity is twice times the frequency squared times twice the frequency squared times the temperature of the gas. And what we define here is EB, which for a few seconds now I'm going to call the brightness temperature. And this temperature is related to the initial black body temperature of the incoming photons through this strangely looking equation. Right? So what is this tau? This tau is the optical depth. What is the probability, more or less, what is the probability that the photon would go through this cloud without interacting? And if I look at the deviation of the temperature that describes the intensity before and after, I get this simply looking formula that has the difference between the outgoing temperature and the incoming temperature is given by the difference from this spin temperature, and here this is why it is a convenient quantity between the spin temperature and the photon or the black body temperature of the incoming gas times 1 minus the optical depth. Okay, so this is just a definition, and because we are dealing with cosmology, temperatures of photons and intensity of photons all redshift, and it is more convenient to define a redshifted version of the above, which we call the brightness temperature. Okay, so up until this point, TB was brightness temperature. Now on T21 is the brightness temperature. Sometimes it is called the redshifted or differential brightness temperature, but in this talk, T21 is the brightness temperature, and it is defined as the difference from T spin at redshift Z from the CMB temperature at the same redshift divided by 1 plus Z times this 1 minus optical depth at the same redshift. So just to be clear, what I mean is the spin temperature and optical depth at redshift Z, all of those are evaluated at a very specific frequency. All those quantities are evaluated at a very specific frequency, which is the frequency of 21 centimeters. Okay. Now we can go ahead and ask ourselves, how is this quantity, this brightness temperature, how does this evolve in time? Okay, so from this equation, we see that in any epoch at which the CMB temperature and the spin temperature are the same, I'm going to see 0. Every time the spin temperature is above or below the CMB temperature, I'm going to see an emission or absorption in this plot of T21 versus redshift. Now the redshift is in the upper y-axis and the actual x-axis I'm plotting here is the frequency, because each frequency I measure, right? So today an experiment would measure an intensity versus frequency, and each frequency is related to redshift Z through the redshifting of this 21 centimeters line, right? So the frequency that I measure is an absorption that I measure at frequency F should originate from absorption that happened against hydrogen atom at redshift 1 by 1 plus Z given this ratio.
So you said before that we're interested only in frequencies which are much lower than the temperature of this otherwise, so that we can approximate it by relations, but here you're assuming that they can be equal.
The spin temperature is not the frequency.
Yeah.
I said that the frequency, the 21 centimeter photons frequency is always much lower.
So the spin temperature is always much higher.
Yes.
But the spin temperature is a measure of what scatters in the hydrogen cloud, whether you scatter against the singlet or the triplet, is that right? So if the spin temperature is 0, you have no scattering in the hydrogen cloud.
It doesn't measure the scattering, it measures how many of them are in the singlet versus the triplet.
Yeah, but your formula for I prime had TS in it, so I put TS as 0.
Yeah, so when TS equals 0, it just means that I only have absorption. That's the reason. Right?
So one is absorption. One is absorption.
Right, so this is the absorption, and this is the emission.
I see.
Okay, that's the reason this comes with the suppression, and this comes with some of those.
So TS just measures whether you have emission, basically.
Right. I would say that what measure if I have emission or absorption, which is exponent, right? So when my optical depth is 0, then I only have right, and when this is 1, then right. So when tau is infinity, I can.
And so, like, if the hydrogen, if the states are actually in thermal equilibrium and this hydrogen cloud is actually at a temperature, then that is the spin temperature. Right?
If I have something that couples the spin temperature with the kinetic temperature.
Oh, but is that actually going to be the case at some points in time, or is that
Even if you assume that you are in kinetic equilibrium throughout the evolution of the universe, which is to some extent very accurate, the spin temperature will deviate from the kinetic temperature. Yes. Okay, we'll get to this in a second. Okay, so just to orientate ourselves along this plot that should represent the age of the universe going from left to right. So this is roughly almost today. Right, today is redshift 0, but certainly in this discussion is going to be sufficiently close to today. And here on the left is basically the initial of the universe, right? So frequency 0 in this definition is redshift of infinity. But what happens here is recombination, and sometime after recombination, at redshift roughly 200, but less than 200, what happens is that photons can no longer maintain thermal equilibrium or kinetic equilibrium with the hydrogen gas, right? So I have a gas of small fraction of free electrons and many hydrogen atoms, but the interaction, the constant scattering of photons with the small residual fraction of electron can keep electrons, photons, and hydrogen atoms in the same temperature. But then at some point, because the universe expands and the number density of electron drops, photons no longer scatter really efficiently with the electrons, and the temperature of hydrogen atoms, electrons, and the CMB decouple from one another, and the gas starts cooling faster because it redshifts like matter, not like radiation. At this point, as you just suggested, hydrogen-hydrogen collision are good at keeping this spin temperature coupled to the kinetic temperature of the gas. The kinetic temperature of the gas is lower than the photon gas, and I see a first absorption in this 21 centimeter in this brightness temperature. However, later on, these gas continue to deplete, and at some point, what happened is that resonant scattering and emission and absorption of CMB photon start flipping the spin of the hydrogen atom more efficiently than those scatter reshuffle them. And what actually happened is that this spin temperature couples back to the CMB temperature due to resonance scattering with CMB photons. Later on, what happens is slightly more involved, but we reach an epoch of the universe called the cosmic dawn, and this is a very nice name because this is where the first stars are born. So we have the first light, just like in the morning, and just like in our more mundane dawn. And at this point, what happens is that light from those first stars, specifically Lyman alpha photons from those first stars, can scatter resonantly against hydrogen atom. The Lyman alpha photon excites momentarily the hydrogen atom into the first excited state, which immediately decays back to the ground state. And in this process, triplet can go into signet and vice versa. And this process, again, what it does, it couples the spin temperature to the gas temperature, to the so-called color temperature of the Lyman alpha photon, which again is just this color temperature is just quantifying the flux of Lyman alpha photon. But because again the gas temperature is colder than the CMB temperature, we see a second absorption. Later on, light from the same stars, specifically in this for the next discussion, UV photon and X-ray photon start to heat up the gas and we see this line going sometimes even to an emission, right? So what happens is that now X-ray photon, mainly X-ray photon, heat up the gas such that it becomes hotter than the CMB, and the sign of this quantity changes. And later on, UV photons ionize the gas, and as they ionize the gas, I no longer have hydrogen atoms, so nothing can absorb or emit those 21 centimeter photons, and I no longer have a line, and the line vanishes when reionization is complete. Okay, so this is the rough picture of how this line should evolve against cosmic time. Fortunately, astro is very difficult, and while initially during this first peak, this is pure lambda CDM with no baryons calculation. Okay, so no standard model other than this hydrogen atom. You don't need to worry about star formation or anything. We don't really know how stars are formed, and once they are formed, we don't really know how to calculate what is the flux to its very different component. We don't really know all the physical processes and all the ingredients that enter the calculation, and so there are many different phenomenological models. So this band I was trying to show here, and I hope it is clear enough, is a compilation of 140 models or something like that from this paper from 2021, where they just go and change slightly each one of those 12 parameters that they have in their model. And this is just an envelope of many different models that they have. Do we know that this is the absolute largest possible envelope? We don't know for sure, though many of those parameters cannot be constrained by any way other than using 21 centimeter observations, but it seems like they were very generous in the kind of parameters that they're using in the range of parameters. And this is kind of accepted as a ballpark of what is the range of possible standard model predictions. Yes.
So when you describe the cosmic dawn to reionization to later, it's a tau of Z that's changing, right?
Yes.
Okay.
Yeah, because at some point what happens is
Density of the neutral gas.
yes, goes to zero. So what will be observed if this program is completed, and it seems like it is going there? What will be observed? So hopefully we will at some point have 3D maps of the universe. 3D because we will have field, which we can say is 2D map times time or redshift, which is the third dimension. And we have a volume that tells us how does the universe evolve. And of course, people have already looked at how new physics would affect those 3D maps. And this is just a demonstration of how such 3D map or slices of 3D maps would change in the presence of warm dark matter with different mass. But this kind of 3D maps still seem far along the way. The more realistic and ongoing observational effort are the experiment that aim to measure the global signal, which is the sky average signal, and the power spectrum, the 2-point correlation of this signal. And I'll start by describing some more advanced power spectrum experiment. I'm going to focus mainly on HERA because this is the leading effort currently. It is led by Berkeley scientists, and other than that, there is MWA and NOFA or its upgrade that will hopefully happens. I don't even know NanoFAR. And I don't want to say much about the technical design and everything, but these are all interferometers because they are aiming to measure 2-point correlation. So they need to have different length scale to access different scales. And they are trying to put better and better constraints on the strength of the power spectrum, right? So this power spectrum, which unlike in the case of CMB, it makes much more sense to measure it to measure the dimension full quantity and not the dimensionless quantity because we don't really have an access to the normalizing factor. So we need the dimension full power spectrum in units of millikelvin squared. And they are trying to get better and better constraints on the power spectrum. But what we can see from this plot is that there are already many measurements, which is a good sign. We have lots of measurements, which means a field is active, and the slightly more pessimistic thing is that we are still far away from all the standard model benchmarks. We are still 2 to 3 orders of magnitude from most conservative, not conservative, more optimistic standard model predictions. On top of these plots, there are 2 more recent measurements from late 2022 from the HERA collaboration, which are again improving slightly over some of the existing constraints. But hopefully within a year or 2, they should, at least in some of these redshift range, they should get closer and closer to the standard model prediction. The end of this talk is going to show how in some dark matter models we can actually get a few peaks that are much higher than the standard model prediction, which will hopefully be accessible to HERA within a year or so. Okay, but to begin our discussion, I'm going to just focus on global signal experiments. So those are simple dipole antenna that aim to measure the sky average temperature. So they don't look at different length scale or anything. They just ask what is the temperature or what is the intensity of those 21 centimeter photons. And yeah, EDGES was the star of the show a few years ago because it claimed to have discovered something that was in tension with the standard model of cosmology. And they say that they find an absorption profile, but this absorption was extremely deep. how deep? So deep that it doesn't fit the slide. Okay, so it was outside, right? So I had a few orders of magnitude of astro uncertainty, and the error bound. So this is like the 2 sigma error bound of the best fit model was something like 4 sigma from the lowest, and 3 sigma from the lowest from model prediction. And yeah, this got people excited because you could put in this big line, you could put a very very loose lower bound on this absorption, right? So it's very, very optimistic. You could never go this low probably because, let's not go into the details now. It is really hard to imagine that this lower bound could ever be met by actual astrophysical model. But even if it does, it was so far away from what we measure that people thought that this must be mended either by astrophysics and cosmology or some new physics. And this is why particle physicists started talking about 21 centimeter cosmology in 2018. Now, what can possibly give rise to such a deep leap?
So sorry, so this pink line, you assume that there's no energy injection to the gas or something?
Yeah, so I assume that I have a mechanism that can couple efficiently the spin temperature to the gas temperature with no energy exchange. So I have some magic glue that doesn't transfer any energy, which I think violate energy conservation. Good. So now people ask what could give rise for, or what could explain this kind of feature, and there is the obvious immediate suspect, which is statistics or instrumental. I'm not going to talk about it, but if you're interested, I have a few backup slides, so you're welcome to either ask me later or just stay and we can talk about it for a bit. Then there is the explanation that, right, so I'm trying to make this number, I'm trying to bring the lower bound a bit lower to where the edges error bound were. So 2 things I can do. I can decrease this gas temperature, or I can increase the CMB temperature. So decreasing the gas temperature is going to be the main topic of this talk. I'm just showing one plot, but we'll get to this same plot later in the talk. So one option that people discussed was cooling down the gas due to scattering with dark matter, which is colder than the standard model. And another option was that you can actually heat up the CMB, and you don't need to heat up the entire CMB because this is the quantity that is really well measured. You only need to heat it up in the low energy tail where this 21 centimeter line or feature might show up. And this was done with astrophysics by questioning the spectrum that astrophysical black holes emit, but also with new physics. And Maxime, who is not around, was involved in this effort immensely. He was the first one to suggest a solution. But before going into explanation, even if you don't explain it with new physics, just the fact that I measure something that is so well beneath any lower bound that I have gives me an information about new physics. Because if I have some sort of energy injection that might heat up the gas, they would violate this kind of measurement because they would push this and they would put this line higher. And just as one demonstration, I have this lovely constraints on light particles or light scalars decaying into 2 photons, and we can see the constraints with edges and without edges, and we see that there is a whole new range of parameter space that could be explored by an experimental technique. Okay. But then an experiment named SARS-3 was launched, aiming to either confirm or refute evidence results. And this is basically what I find. Okay, so they find noise consistent with 0, and if they try and ask how unlikely is how much do they disagree with edges, they find something like 2 sigma. And you might think, okay, in green I'm showing the 99 confidence interval. And you might think that if I have here more than 99, here and here and here, this looks like much more than the 2 sigma I'm quoting here, but the error bars of this green band are highly correlated. There is like a polynomial hiding some of them. But if you go and do the statistics right, with and without the edges modeling, they claim that they have somewhere between 2 and 3 sigma exclusion of edges finding. Okay, so why am I still talking about it? I'll say soon that there are still reasons to be thinking about cosmology. And the other reason is that I think that the way Sarah's analyzed the data, and which is similar to the way edges analyze the data, it has, I mean, you need to have some substantial amount of faith to think that this would actually, right? If you see something, you see something. But if you don't see something, and to believe from this kind of analysis that this method of foregrounds of pattern, yeah, I have it also in the backup slide, but you need to do something like 4 or 5 orders of magnitude of foreground subtraction, where you don't have a model, you just feed it to a polynomial. And you need a large amount of faith to think that this could actually tell you all the physical story if you don't have a well-established physical model for this foreground. So they both use the same technique, and I don't really think this is the best way to go here. I think that power spectrum experiments are much more reliable, and that's the reason we are getting there slowly. But I just want to say that even if these edges, even if these Sarah's or something similar to Sarah's measurements are correct, there is still things that can be said about particle physics. Those results or conclusion about particle physics would be much more dependent on astrophysics and uncertainties. But basically, if you have a model that tries to explain edges, it would also be in, and this green band does not agree with edges. If you have a model that pushes your measurement below this band, you could set constraints with this. And this is like the glass half full part of this story, that if we have something that tries to bring the line the brightest temperature below this error bar, we could probably set constraints. And this is an ongoing project with some folks in Tel Aviv and Diego. Okay. But more generally, the question I want to ask is, what can 21 centimeter cosmology teach us about particle physics? And maybe more specifically, I want to ask whether there are models that are models that make sense to some extent, at least. And they could cool baryons, and they could imprint this 21 centimeter line. Maybe this is a good time for questions before I move on.
But are you trying to solve a problem when you do this more general here, or you're just trying to add physics that you can see a signal?
No, so basically I'm going from now on, assume that there is no problem, but I'm going to, but I know, because of trying to address this problem originally a few years ago, I know that there is a huge experimental program that is being built, and I'm trying to see if we can harness it to study particle physics.
So you'll just add some physics in there to see if we can see it. But,
yeah,
but the physics is not needed for anything right now. It's just to create a signal, is that right?
Right. But I'm not. I'm trying to do something slightly more general, as you'll see in a second. I'm trying to ask what could ever possibly leave any from this kind of right. So I'm not necessarily saying this is a model. I'm trying to go to a larger model space and see if this is a tool that can be actually used to study new physics. Because there were claims like that before, and I'm going to slightly question it.
Just out of curiosity, so the edges line is pretty smooth, but the Sarah's line is very big.
Right. So
is there any reason?
So the reason is that I didn't sit down to digitize the edges actual noise curves, but sorry, the noise results. What they do is they fit to a model and they give you 2 sigma lines. I could have shown lines that are similar, that are very similar to Sarah ones.
I
But
see.
they do show, they look similar to the fitted model.
I see. So it's more like how they present the result.
Yes.
Are the foregrounds that you have to worry about mostly atmospheric? And if so, are there like attempts to do space-based 21 centimeter observation?
Yes.
Oh.
To both your questions, yes. So those are mainly, sorry, not atmospheric. Many of them are synchrotron, but the atmosphere is a huge burden on those pyramids, and therefore there are also, yeah, it's right, radio astronomy, and Earth is probably the worst place in the universe to conduct radio astronomy experiments, right? It's probably the most the worst. There are more radio loud regions in the universe. But yeah, so there are proposals, and some of them are even almost in the Pathfinder phase of sending something to the dark side of the moon. But yeah, it will not get rid of all the program, but it will get rid. It will help bypassing a lot of limitations. Okay, so for this discussion, I'm going to assume that I have some hidden sector particle that I'm going to call chi, and it has a temperature of some sort, T chi. It's going to have mass density rho chi, which comprises a fraction F chi of the dark matter density, and I can also write it in terms of normal. Then in terms of density normalized to the critical density, and the number density n.
What do you mean by temperature for this?
Yeah. Yeah, so for now, it is just a measure of the energy, kinetic energy of this sector, but almost always it will have some amount of collision, either within itself or with dark matter particles, or with standard model particles that would push it into action within itself, not necessarily. You'll have some collision that would make this small fractional particle. F is going to be small. Okay, so one statement that I'm not going to prove is that the cross-section has to scale like a velocity to the -4. The reason is that the velocities at the epochs that will go in the relative velocity between dark matter, standard model particles, or hydrogen atoms in the epochs at which we're going to be interested is going to be very, very small. So v to the -4 enhancement in this case, something similar to Rutherford scattering, is actually a good thing because it makes the cross-section large precisely in the epoch we want it. Precisely, well, relative velocity between particles are the smallest in the evolution of the universe. This is a good thing because it means that it will impact this 21 centimeter observable without impacting other things like CMB, or right. It allows for a large cross-section that would otherwise be excluded. If I try to do it with any other velocity dependence, if I try to assume that this is some kind of a constant cross-section, it would be excluded by infinitely many other considerations, be it collider physics and stellar cooling, CMB, depending on the model details, but it is quite generically a simple argument that anything other than v to the -4 is guaranteed to be excluded.
But what do you mean exactly? Like -5 is also not allowed.
-5?
Yeah,
Oh, I don't know how to get more than -4.
it's more okay. It's more like a model.
What?
It's more like a from the model consideration.
You're asking why am I not going to log? Yes. So I want this power of velocity to be as negative as possible.
Yeah.
But within reasonable or simple this models, I don't know how to get to low.
Okay.
Right. I don't know how to make
Sure. I understand that.
good. Now, in order to affect anything, in order to cool down my standard model path, I need to have some kind of cross-section. So I know that my cross-section versus mass parameter space is bounded from below by something. Okay, I'm just going, this is going to be a very rough picture and we'll show number later. Now, with some very preliminary and with very simple thermodynamics argument, I know that if I change the kinetic temperature by some order 1, the gas temperature by some order 1, I need to heat up my dark matter particles by an amount that conserves energy, right? So the total thermal energy is number times temperature. So I get a good estimate of the temperature of the dark matter after I cool the baryons. Now, in order for this temperature to be able to cool down the kinetic temperature or the gas temperature, I must have that this high temperature is lower than the gas kinetic temperature, which allows me to get an upper bound on the mass of my particle chi. So from very simple thermodynamics argument, I see that the mass of my particle should be lighter than 6 GeV times the fraction of dark matter that it comprises. So this bounds my parameter space from the right. Now, from the left, I can bound this parameter space by stating the cross-section needed in order to leave any kind of imprint on this 21 centimeter line is large enough such that it must be produced inside stars, and from the fact that and we have constraints on the mass of dark matter particles if they can be produced in stars, so the constraint this chi must be higher than roughly 100 keV. If you have 100 keV particle with such large cross-section, you might worry also about PBN, which kind of generally would push you to around a lower bound of 10 MeV, but depending how much model gymnastics are you willing to do, those can be circumvented. So there are models in the literature that allows for massively lower 10 keV. But this is just to say that we have a parameter space that is bounded from the left. Just for the time, sorry. Okay, next I'm going to say that this parameter space is also bounded from above by fifth-fourth considerations. And the idea is very simple. If I have something that makes any standard model particle talk with my dark matter particles, it also means that I have some, okay, and it gives me a velocity dependent cross section that scales like e to the -4. I also get a fifth fourth between standard model particles and themselves, right? So I can ask what are the constraints on such a fifth force, and I'm just going to use the fact that I want this chi to behave as a perturbative particle. So I'm saying that its coupling to this new boson mediator is smaller than 4 pi, and it allows me to translate the required cross-section in order to affect the 21 centimeter whatsoever, and I can ask what are the constraints on such a fifth force. And if I look at the plot of the mass of this new mediator versus this effective fifth force parameter, I see that without doing further model building, I'm quite always excluded by many orders of magnitude. So this is a plot we made when edges came out, and we asked if I have something that makes dark matter, that this is the entirety of dark matter, talk with any one of the particles, which is hydrogen, helium, or electrons in the gas, and what is the required cross-section? And the cross-section is quite large. Now, if my particle is not all of dark matter, it would just push those lines even higher, which would be even more excluded than that. Now, what is one caveat that you could find, or one way around this kind of strong constraints? You could assume that your particle or that the interaction is proportional to the electric charge. Why does this open a parameter space? Because things that constrain fifth force are electrically neutral. So if my force is proportional to the electric charge, and my experiment is built out of neutral objects, those constraints will no longer be applied. The only thing that would be applied again is the production of those mediators in stars and stuff alike. So how do we get a very small effective coupling that behave like an electric charge? Well, usually with a hidden photon sector and some kinetic mixing with our regular photon. So it is possible to get small charges without violating Dirac quantization, for example. Okay, so it seems like particles that appear electrically charged are the only viable solution. And within this framework, we couldn't find any exception, and we tried for a while to find a model that interacts, that can cool down baryons by elastic scattering, and is not violated by, and it is not excluded by any other measure. Good. So,
sorry, just interpreter without. When the coupling is proportional to charge, it seems you have viable solution. Why do you say you don't have any viable solution?
yeah, so I'm saying the only viable solution. Yes, so I'm saying something that looks like electrically charged particles is the only solution we could come up.
And does it matter on your force mediator being a scalar or a vector?
No, because those are like very low energy scatterings, so they behave the same, right?
And all the constraint calculation does not change.
Those fifth laws are always, these are constraints on the potential, right? So the long range potential, the momentum transfer is. The stellar cooling bound might be fair.
Yeah.
Okay. So after we draw this conclusion, people started looking at this parameter space slightly more seriously, and those people specifically, Eli Kovetz and company, showed that okay, there is this thermodynamic constraint that we said, but there is also a constraint on how small f should be. So if I have a fraction of dark matter that is electrically charged, it is not really dark matter. And actually, this kind of charges that we need are so strong that these particles are actually part of the baryonic fluid during CMB. So effectively, what I'm changing here is omega baryon at the time of CMB. So whatever energy fraction is in the form of those new particles, it should be below the uncertainty to which we measure the density of baryons in the CMB. So this puts an upper bound on the fraction of particles, the fraction of dark matter that is in the form of charged particles. So these two numbers together constrain it not only to be lighter than 6 GeV, but to be lighter than 6 GeV times 4 10 to the minus 3. Which makes this parameter kind of small. Now, if you go and try to do the VDN calculation slightly more precisely, and you ignore this exception that people have found, this parameter space is shrinking drastically. And you have only a very tiny regional parameter space that is not yet excluded, but hopefully will be excluded. And yeah, okay, I just wanted to add that the bound from above of this parameter space is coming from the slack militia experiment. But then we realized we can do slightly better by extending the model a bit. And what we did is to introduce some new form of interaction between the charged particles and the rest of cold dark matter, right? So the model becomes more contrived, but we are trying to be optimistic here and say that we can do something with 21 centimeter cosmology and tell something about particle physics. Now, the idea is that initially during CMB, as I said, the interaction between those chi particles and baryons is so strong that chi is effectively part of my fluid, my baryon fluid. Later on, for some reason, it leaves the baryons and starts flying towards the CMB fluid, and by the time at which we measure the 21 centimeter signal, we want this chi particle to already be tightly coupled with the cold dark matter fluid. How do we achieve this? We notice that there is a huge difference in the amount of.
So chi is not really related to the cold dark matter now. So you have separate cold dark matter and chi.
Also, yeah, also previously we had to, right? So as
right,
said,
because of the 0.4%.
right.
But this doesn't fix that.
Yeah, now I have no reason for it to be large because I have the rest of dark matter in another.
Okay, so you're not, this is not having anything to do with a candidate for dark matter. This is just to explain edges now.
Right,
this
so
is-
you are
you're just
questioning
adding a
my
new-
title. So it's not dark matter, baryon interaction is something baryon interaction.
Right,
I
okay.
agree. But I mean, dark matter, still around, we're still talking about dark matter. And
Wait, sorry, is this supposed to help you get around the 0.4%?
it's
Alright.
supposed to allow me to go to much higher masses, as I'll explain in a second.
Okay, but like chi is still part of the baryons during the
Yes,
CMB,
chi
so
is
you're
going to
still.
be a sub 0.4% of dark matter. It's going to be a tiny fraction of my metal content, of the universe metal content.
Okay.
Okay, so how does it help me? The interaction between baryons and sky particles are enhanced at small velocities like e⁻⁴, but they are suppressed by the residual fraction of free electrons because charged particles talk mainly to charge electrons and protons specifically, proton in our case. And XE at the time when we measure things is very small, it's around 10⁻⁴. While if I assume that the interaction rate between chi and cold dark matter is just proportional to e⁻⁴, I get that the ratio of those two interaction rates can initially be very strong. So the ratio, the interaction with baryon is much stronger than the interaction with cold dark matter, and later on they switch roles. And this is how we can realize this kind of thing. So basically, just by introducing long-wave interaction between this dark matter and baryon, we get this behavior for free. What do we gain by this? This energy conservation argument that I made before is slightly altered because now on the left-hand side, the heat is not shared only among chi particles, but the heat that I absorb from the baryonic fluid is now shared among the entire cold dark matter fluid. And if you go and do the same exercise, you basically get that you have this new reduced mass. So, and this new reduced mass is bounded from above by 6 GeV. And as we said, this F is going to be so small that you could just replace this mu by the mass of cold dark matter. So basically, I'm now pushed to a model where cold dark matter is lighter than 6 GeV, and M chi could actually be quite massive. Good. What does it buy us? What in terms of parameter space? It generates a model where you have a small fraction of charged particles that interact so strongly that they don't make it to the direct detection experiment. The interaction, the charge is so large that they get stopped in the atmosphere. And if not in the atmosphere, in the Earth's crust, but they don't leave any imprint on the direct detection experiment because this is the direct detection experiment can only probe below this point. And still it is in some of the parameter space small enough to not be produced or probed or constrained by collider and beam experiments. So we found a new model that leaves some here just by increasing the heat capacity of those charged particles by letting it interact with the cold dark matter. Okay, now we can in principle close the loop of those charged particles, and then we get effective interaction between cold dark matter and baryons, and then you can ask what would be the detection constraints on that, and I can show a plot, but there is still a viable parameter space quite large. Okay, and now the topic of today's talk. I wanna present one signature that is, I think, slightly more interesting and slightly more trustworthy for this kind of moment. And I'm going to talk about, so the smoking gun is going to be in the 21 centimeter power spectrum, which I haven't discussed so far. I'm not going to go deep into the details of the calculation or anything, but just try to get to the results as fast as I can. But basically what happens in the early universe is that baryons are, I didn't give this disclaimer. When I say baryons in this talk, I do not mean baryons. I mean hydrogen atoms, electrons, protons, and anything in front of model that is not photon or neutron. Why? Because this is the language cosmologists use, and I don't know. I moved to the dark side or something. So yeah, so there is strong interaction between photons and baryons, and they move together. And meanwhile, dark matter is much slower, and it starts falling into over density starts collapse. And what happens is that in general, at a given point in space, you are very likely to have a relative bulk motion between the dark matter fluid and the baryons and photons fluid that are moving much faster compared to even after photons and baryons decouple. Still, there is a relative bulk motion between baryons and dark matter, which is denoted by this VDC. This description should be familiar to anyone familiar enough with baryonic acoustic oscillation, because it is sourced in a similar way, model with the arguments about pressure and stuff. But basically, photons and baryons were coupled. They were moving relativistically, and even after they decouple, they still have some velocity relative to dark matter. And this dark matter, and at redshift of 1000, which is the initial condition for our calculation, it has a normal distribution with VRMS of roughly 30 kilometers per second, and it has a power spectrum with a very distinct acoustic peaks features on it. So how does it enter our calculation? Now it's a good time to do this. So how does it enter our calculation? When I look at the temperature evolution in the presence of dark matter and baryon interaction, I have a very much expected term, which is something that tries to thermalize the gas and the cold dark matter temperatures. But there is also another term, which is a drag term, right? So even if I imagine two fluids moving with respect to one another, they have the same temperature, but they interact, and they move with respect to one another with a certain temperature. As they go through each other, they have some kind of friction, right? So they are colliding and they are trying to slow down, and at the end, right? So if I have two fluids that are colliding constantly, at the end result would be one fluid which is slightly hotter than the fluid we started with, right? So this drag term will actually heat up. Right, so basically, the way it affects our calculation is the result would be that regions in space where the bulk motion is higher would be hotter than region in space where this relative motion is low or zero. Okay, it happens actually due to two effects. One is the fact that I have this new heating term, this drag term that heats the gas, but also because my interaction rate, the thing that is responsible for cooling, is very velocity dependent. So regions where the relative velocity is larger, the interaction rate is going to be relatively small. Now, people have looked at this effect before, but only for models that are already excluded. But we did it in a more realistic, well, I don't know, realistic is up to is up for debate, but for an unconstrained model, not yet excluded model. And we also included the effect of different astrophysical processes, and we try to scan over a quite large set of astrophysical models and ask how large is this power spectrum going to be, and compare it to the lambda CDM prediction. So if we look at this green band or yellow band, I don't know, I'm sorry, which is the envelope showing all different standard model predictions people have studied, we see that our model, depending on the charge of this dark particle, quite generally predict larger cross sections, larger power spectrum. And maybe the plot I like the most about this paper is the following one, which I'll say the bottom line and then explain it. The bottom line is that we are able to show that regardless of whether you trust the way global signal experiments conduct the foreground construction or not, it is very likely that a signature of this kind of model that allow for dark matter baryon interaction would show on the power spectrum far before it would show any kind of signature on the global signal. So basically what we show here is the power spectrum at a fixed scale versus the global signal, the sky average one. And as we go from top left to bottom right along this curve, what we actually do is increase the charge. So we see that even relatively small charges, depends on the value two, once again, smaller compared to one, smaller compared to one. Okay. So relatively small charges starts by making a deviation in the power spectrum, and only later on we see more significant change to the global signal. So only charges around here start entering the band that edges thought a signal could appear, but this kind of signal would be long excluded by either nanofar or HERA. So the take-home message from this plot is that power spectrum experiments are very soon will be much better probe than global signal experiment, this kind of dark matter baryon interaction models. One thing that I will not say, but you are welcome to ask if you want, is that those power spectrum experiments, in my opinion, are also much more advanced and trustworthy in terms of foreground subtraction and removal. And with this, I come to my conclusion, which and the most important message is that astrophysics is complicated, so it makes things hard, and it's not so easy to discover new physics. And the interesting point that we were able to show a few months ago is that it seems like power spectrum experiment will be able to tell us something about the only model that we think could ever leave a signal for 21 centimeter cosmology within this framework. Thank you, and sorry for.
Thank you for the great talk. So questions?
So you mentioned that there's an exception for the bound from BBS. So what exactly is that exception? How do you avoid the bound?
So basically what they have, and I don't remember all the moving parts, but basically what they have is another. So the way they get the mini charge is through Spuckelberg mechanism and not even photon mixing. And what they have in order to avoid BBN is another scalar which acts as an entropy dump for those charged particles that is kept in thermal equilibrium with those charged particles in the early universe. And this whole sector is called by the logical number of 2, right? Because if you have another light scalar in thermal equilibrium, it is enough to make it a factor of 2 quarters in CMB to avoid current BBN constraints. So this is what they haven't done enough.
I see. Okay.
Any other questions?
Yeah.
So your whole analysis seemed like you were trying to see how can we possibly get some absorption of the spin temperature, or like some lower spin temperature. Have you thought about models which could give you an emission?
By scattering, you mean, or in general?
Or in general, just something that would give you like a positive spin temperature instead of negative?
Yes. So the obvious candidate would be energy injection of some sort, right? If I have decays or annihilation into any electromagnetic particles, it will heat up the gas and would generate an emission. The global signal would be just an emission. The power spectrum, it would also be smearing of the power spectrum, just because dark matter is more isotropic than galaxies. So, so in principle, once we have those measurements, yeah. So unfortunately, there were 2 camps when these edges things came out. the camp of people that saying, okay, let's constrain physics with it. And there were the other camp, which I was part of, which is let's explain it. And I think that the explanation effort has proved to be less beneficial. Right? I wouldn't put my money on it. In general, right, this is always the right thing to do. Never assume that your model is right. But I think that the energy injection constraints from 21 centimeter measurements, once those are available, are going to be great. It's going to be an extremely sensitive probe of energy injection throughout very wide frequency.
And for those signals, do you think the global signal is better or the power spectrum?
I don't think the global signal is better than anything. In general, I just think it's so. Just show. As long as I say that I don't really trust the foreground subtraction, it's not a matter of trust or not. It's, I really believe that this is the way we can get rid of this foreground. You will always be with something that is a band of size the standard model production, right? Now, in order to exceed it, you need your dark matter to produce more light than stars. Do you think it's a good investment of dark matter model? Right, so you need a lot of light. You need to exceed, right? Because this band is set by light emitted from stars. So as long as you don't measure, as long as you don't have a signal, it will be very hard to explain energy. This is not the argument for power spectrum is very different because stars are in galaxies. They obey a very specific spatial distribution. Dark matter is more is smoother, so you would see a different power spectrum. And also the problem avoidance is smarter.
Not as speak again. We are planning to go to dinner, so if you are interested, then the program go to Caspian. No, sick. You have something?
Let me think about that.
Okay.
Yeah.
Okay.
Yeah, I'm interested.